first speaker on this training school, and one of the questions I had before I came here, what would be the right level of the training. And I see that's a very difficult question. Still, we have many people who are more experienced than me in this topic, so I would have certainly a challenge to tell something new to them, but I also see many new faces, and so I'll try to be as elementary as I can be today, and I will adjust for the two lectures on Wednesday and Friday, but this means that feel free to ask me any questions, however stupid or complex they are. So this would help me to find the right way to speak about Cartan connections. As a disclaimer, I'm not going to speak much about philosophy behind Cartan connections, and I hope there will be other talks who would explain more about motivation, how this appeared, what this means in applications in physics. I hope by the end of these lectures you will see yourself why Cartan connections are so powerful tool in differential geometry, and I will use a lot of examples coming from, well, my favorite topic, geometry of differential equations. This is the very first slide here, and this is just a very short historical remark. What we call today Cartan connections was introduced by Élie Cartan, and he called them generalized spaces. And essentially the ideas and the concepts and actually many initial results originate from these three papers on affine connections, on conformal connections, on projective connections. And if you look at the dates, they come from 1923, 1924, which means that we are right now at exactly 100 years after the initial concepts were introduced. So historically, historically Cartan used indeed a slightly different, different language, and I will use exactly the language used by Cartan, and mainly today especially I will speak, I will just more or less present this paper from 1924, projective connections. What was happening afterwards, we got another fundamental work of Erisman, who introduced the notion of principal bundles, and this is the language commonly used today. Well, if you look at the modern definitions of Cartan connections, they are based on the notion of principal bundles. For those who wants to have some handbook at hand, I recommend this book that works. This is a standard standard today book on Cartan geometry, and a lot of explanations and details present in the book. So that's what was happening before and now, and I'll move right away to some notation I'll be using across all three lectures, and this is like a prerequisites. I hope they're not blocking you from understanding what I will be speaking about. So one of the main objects in the talk will be graded Lie algebras, finite dimensional, so this is just a Lie algebra equipped with a grading that is compatible with the Lie bracket. We will sometimes use the notion of filtration, so when we group graded spaces together, this gives us a filtration, and this always plays an important role here. In fact, a lot of things I'll be speaking about may be told without grading at all, but I'll use graded Lie algebras from the beginning. Another disclaimer: I'm not to people who have seen a lot of Cartan connections in the scope of parabolic geometry. I will not assume that G is semi-simple. though the examples, at least today, will be exactly of this kind because I'll be speaking about projective connections. Then another notion is like negative part of G, which will be often used in the talks, which is just the sum of all graded spaces with no negative degree, which is a graded nilpotently algebra. What else? Well, I don't think I can. I think.
Sorry.
Yeah. I think we have conflicting houses.
The microphone is at the same time the camera. It's preferred.
Maybe it's better.
It's still pointers here, but there's. I cannot navigate any longer.
You have to click into the window.
You can click into the window.
Yeah,
But Boris can't.
No, not you.
Okay. Yeah, thank you. So then, by capital G, I'll denote the Lie group with the Lie algebra G and some subgroups. So in particular, if I is positive, then this filtration is also a Lie algebra, so we'll have a subalgebra, then we'll have subgroups. And another important subgroup will be G0. The main actor will be a homogeneous space. Homogeneous space of the Lie group G and the stabilizer G naught, when not, well, G0, well, this is the sum of all this is a subgroup that corresponds to a non-negative part of G. This is a homogeneous space, and as we'll see very soon, Cartan connections are modeled by homogeneous spaces. So this is a homogeneous space I'll be using all across the top. Again, I know that in parabolic geometry, this G0 is often denoted by P because it's parabolic. In my case, it's just a subgroup on G. And the last piece I'll be using across all the slides is the Marais-Cartan form on G, left invariant Marais-Cartan form, which is denoted by theta in my talk. So that's prerequisites. I would have probably put it somewhere there on the table or on the blackboard, but it's not many. And right away, I'll go through a modern definition of a Cartan connection. And you'll probably see it many times today and tomorrow in other lectures. This is exactly the definition of Ehrmann, and this is not what was used by Cartan. So I'll switch to Cartan's language fairly soon. But just to give you a feeling of rigorous modern language, so what we have here, a Cartan connection on a manifold that is on a manifold M modeled by a homogeneous space is a principal bundle and the one form, which takes values in G. So, and these are three properties. So essentially the properties are that omega takes vertical fundamental vector fields to the corresponding elements in the Lie algebra. It is equivariant with respect to the right action of the subgroup G0, and most importantly, it's a vector space isomorphism, so it's a parallelism on the bundle. Again, if you see this definition first time, don't be afraid. I'll switch to another one fairly soon. If you know this definition, you'll also, it will just a reminder of the notation what I'll be using here. And of course, the main example, and this is what I'll put here on the blackboard, the main example of such Cartan connection is a homogeneous space itself equipped with the bundle, and omega is just theta, so left invariant Marais-Cartan form. So whenever we have Cartan, whenever we have a homogeneous space, we always have an example of a Cartan connection, And if you, and of course, all these three properties are satisfied by Cartan form, but we just require a bit less, because essentially in first and second property, we have the requirements limited only to subalgebra G0 and subgroup G0. While, of course, left invariant Cartan form satisfies the same properties where X is in G and in the algebra G, and right equivariance is also with respect to all right shifts on the Lie group G, not just on a principal subbundle. So one of the philosophies, if you like, behind Cartan connections is to weaken a little bit the properties of Cartan form on a Lie group. But that's probably not exactly the right point of view, but well, we'll see how Cartan defines this. So I mentioned already that Lie Cartan's definition it's generalized, in at least Lie Cartan's words, that was called generalized spaces. And to now bring you to the language Cartan used, let's do the following. Let's fix a section of our principal bundle on which Cartan connections live, and pull back everything, all the objects, down to the manifold M. So in Cartan's notation, everything was on the manifold M itself, not on the principal bundle on top of M. So this is what we are going to do now. And to pull down everything to the manifold, we need a section. So we fix a section on, of course, on a certain open subset. So sections, well, our principal bundle might not have global sections. And I'm not able to move forward yet. Okay. So what happens if you have a principal? What happens if you fix a section? First of all, principal bundle can be trivialized. So we can identify our principal bundle over our neighborhood U alpha, with just a direct product or trivial principal fiber bundle. So it's U alpha times G0. It's again the standard way you deal with principal bundles very often. And you know that if you choose a different section, maybe on different neighborhood, then on the intersections, on the intersection of this neighborhood, you have what's normally called transition function that relates sections S alpha and S beta. So they might differ, and the difference is measured by a function that is defined on the intersection and intersection of neighborhoods and takes values in the subgroup G0. So this is a transition function, or it will be also exactly gauge transformation that will be used very often because sections are not unique. So sections will be defined up to such gauge transformations. Now, and actually, one of the ways to define principal bundles is to cover your manifold M by such open neighborhoods U alpha, define sections, trivialize, and then you have these transition functions that satisfy natural co-chain property, and this is one of the definitions of principal bundles often used in the literature as well. So if you have such trivialization, we can take pullback of a Cartan connection and have it defined directly on our neighborhood U alpha. It's still a one form with values in G. And if you now see what happens if you apply gauge transformation, or if you move from one section to another section, then this one form is changed according to this fairly simple rule. So one important thing here is that we have a linear part. So this is a joint action of element or function taking values in G0. So this is a linear part, and this is somewhat differential part. So it's a pullback of a Marek-Cartan form from G0. What is really important and what will be often used is that the second part affects only G0 part of form omega. It does not affect everything that lies outside of G0. So outside of G0, the action is really linear. So in fact, this is exactly how Marek-Cartan, how Élie-Cartan envisioned, generalized spaces. For him, these were one forms, or one form, if you stick to a fixed section, that was a one form on all M, or just on an open subset of M, with values in G, that you can transform according to the soul. So you are free to choose any function psi, transition function. This means you change your section. Then your form changes according to the soul. And this formula is very well known also in the theory of linear connections. This is exactly how linear connections change according to gauge transformations. The difference is exactly as I mentioned, so that omega takes values in G, but the second term takes values only in G0, and the function psi also takes value in G0. This is a key difference between linear connections and Cartan connections, if you wish. Yep.
So just to clarify, is that one form valued in G or G naught?
In G. That's very important. So omega Cartan connection takes values in G, always in G, not in G naught. But the gauge transformations deal with with functions which take values in G naught. So that's a game that is, and that's actually a core difference between linear connections and Cartan connections, and why these objects are really have different stories, so to say. So. And here, of course, also a Marek-Cartan form on G naught. Okay, so what you can do here, let's start looking at the very, very first example that was introduced in Élie-Cartan's paper on projective connections. So let's now look at projective connections from this point of view. How would this look like? I need a Lie, first of all, I need homogeneous space. So, as I said, so behind any Cartan connections there is a model homogeneous space. In this case, model homogeneous space is a projective, n-dimensional projective space. So it's a projective, it's an n-dimensional manifold viewed up to the projective transformations. The Lie algebra G is exactly the Lie algebra of the group PSL n plus 1. So it's n plus 1 by n plus 1 traceless matrices, trace-free matrices, and this is the grading that we would use to define, to deal with projective connections. Again, it's probably easier if we have it like that. So we have this split of n plus 1 by n plus 1 matrices, where x, y, and z correspond to the grading of this Lie algebra. And it's very easy to check that's indeed the grading. Now, if you take any section, as what Cartan was doing, so instead of working on some big bundles, let's start, right away fix a section, and then turn omega into just a matrix of one forms on the manifold M itself. So a Cartan connection will be just an SL n plus 1 valued, one form on an n-dimensional manifold. That's it. modular gauge transformations we've seen on the previous slide. So this is exactly how Cartan viewed projective connections, if you wish. So it's one form on the manifold M itself. You don't need to go to a bigger bundle, but you have this bigger bundle implicitly because you have gauge transformations that you can use to change your form. So, what you can do with this thing and how you can recover, some classical notions from projective geometry. So, first of all, one of the things you can use, you can do some computations in coordinates. And so you can fix any local coordinate system and represent these forms very explicitly in this coordinate system. So it will be just a collection of one forms in a fixed coordinate system. What else you can do? So you are now allowed to do some gauge transformations. And one thing you can do, and you can check this immediately, is that if you choose a section, you can modify your section by a part that sits in G0, that you can always assume that this -1 part is just dxi's. So you can always adjust your section. If you fix coordinate system, you can always assume that this part is just dx1, dx2, etc., dxn. Again, there's nothing invariant here. It's the simplification you can do if you fix a coordinate system. Fixing coordinate system, start applying your gauge transformations. So gauge transformations are, as I said, so they are really linear on the complement to G0, so they will be linear transformations on this part. So you can always find this linear transformations that brings your N4, N1 forms to this form. So it's dx1, etc., dx2, dxn. So it's already, so we are trying to reduce the complexity of calculations if you're trying to do some calculations with Cartan connections. In this particular case, instead of n plus 1 squared minus 1 forms, we are left with n forms less. So we have a bit less. And this actually defines our section, or uniquely up to transition functions that would now take part only in G1. Well, you can still do better. So you can still use this G1 part. Okay, so I'm sorry, the last line was gone, but I'm here. So again, you are still allowed to consider transition functions that take values in G1 part, which is this one. So now, if you choose these elements carefully, you'll see that you can make this slot to be 0. And this will uniquely determine your section. So if you have a coordinate system, you can fix your section uniquely. And of course, you're left with omega ij's here, omega 0j's here, and the sum of omega i's will be 0 because we are in a traceless situation. Again, that's quite handy because if you do some calculations, you'd want to have less functions. It's always better. And from geometric point of view, that's the same Cartan connection because we haven't done anything but used gauge transformation, and this is an equivalence we have always behind Cartan geometry. So this is an example how one can. What kind of?
Special effects.
Okay, so no, not yet fixed. Yes, I think that's fine. So this is one of the tricks you are always playing when you're dealing with explicit coordinate representation of Cartan connections. So you try to fix a section to make your forms look a bit nicer in a given coordinate system. The next idea in Cartan connections is the notion of development of curves. And this is what I'm heading to starting from this slide. I'll first give, as usual, a modern definition of a development of curves, and then we'll show you how Cartan was looking at this notion. The concept of development is the following. So if you, in classical linear connections or connections on classical connections, not Cartan connections, on Riemann connections on principal bundles, you have a notion of a horizontal lift of a curve. So whenever you have a curve, you can always lift it on the bundle by fixing your initial point. So here, in case of Cartan connections, this works even better. So whenever you have a curve in your space where your Cartan connection is defined, you can define the corresponding curve in your model homogeneous space. So you can, that's called develop. Again, the term belongs to Cartan. So you take so you have a manifold where your Cartan connection is, and you have a model homogeneous space. Well, now, if you have any curve here, show the x of t here, you can develop it to another curve that's now be in your model homogeneous space. That's called development. And as in case of classical connections, this horizontal lift is not unique. You have to fix a point, at least one point at the fiber from which you start your horizontal curve. Here, this development also is not unique, but it will be defined up to the action of G. So this curve will have sense only up to the action of a group G on this model homogeneous space. So how does this work? So the standard way to define it is the Riemann way to define this. Let's put it like that. So the Riemann way to define this works like that. So you first make your principal bundle larger. So initially it was only G0 bundle, so you turn this into a real G bundle. Then, I believe I have to click here. Yeah. So now you extend one form, Cartan form to G bar equivalently, and then G bar omega bar becomes a connection form, classical connection form on the principal bundle. So there is a relationship. So there is a way to construct usual connection from Cartan connection. Though you have to that carries a lot more information with this itself. So in particular, we have a horizontal bundle. Now, kernel of omega bar, as we do it in the classical connections case, will be a horizontal bundle. So actually, if we again go back to, so to say, coordinate definition of connections, Cartan connections, but also connections in principal bundles, in fact, these two connections in coordinates are defined in the same way if you fix a section. So if you fix a section of G, then it can be viewed also as a section of G bar. And then by definition, pullbacks of omega and omega bar are the same. So if you look at this from the point of view of like gauge transformation definition, so to say, of connections, that they are defined by the same forms. with the only exception that in case of this bigger bundle, G bar, you would now be allowed to use gauge transformations or that take values in G, not just in G naught. So that's what happens. Well, anyway, so why I need this bigger G bar is because this G bar can be mapped to our model space, G by G naught, globally. So it's a global map. And this is a definition. So you just quotient by, so here you use G0 to make G, to replace G0 by G, but then you quotient by the right action here. So you use here left action of G0 and G. Here you use right action. And well, this is a well-defined, you can check that this is it's an exercise to check that this is indeed well-defined map. And that's a G0 equivariant. So what would this mean? That it's actually G equivariant, not just G0, sorry. So what now we can do, we can have an easy definition of development. So if you have a curve in M, we lift it horizontally to G bar, and then, and of course it's defined uniquely only up to the action of G, because that's G is a group of our bundle curved G bar. And now we project it to M0, and this is called a development of curve, initial curve X of t. So this is exactly a response definition. It uses it heavily relies on this notion of principal bundles and the correspondence between Cartan connections and connections on principal bundles. So if you like this language, this is how it's defined. Now let's look at how Cartan defines this. Again, we don't want to deal with principal bundles. We want to define everything on our base manifold M. So for this, we need a section. So as usual, we pull back our Cartan form back on our manifold M or neighborhood U alpha on M. We assume that we have a curve that we want to develop inside this neighborhood. So what we do, we apply our one form to have a curve in the Lie algebra G. So omega is a one form on M, omega alpha, so pulled back omega, is one form on M, valued in G. We have a curve, we take derivative of a curve, tangent vector, apply omega, get a curve, now inside the Lie algebra. So whenever we have a curve inside Lie algebra, we can have a curve, the corresponding curve in the Lie group. So that's again the very standard trick one uses a lot in the theory of Lie groups in Lie algebra. So whenever you have a curve in Lie algebra, you can always have a curve in the Lie group. And it's defined by a differential equation though, so you have to be careful. So the notion of development requires you to solve first order ODE here. That's an ODE written here. But now an easy exercise, and that's a good exercise for tutorials. So if one wants to do some exercises, is to show that actually the development of our curve X of t is exactly given by the action of this curve G of t in the Lie group on the origin. So it's G of t, G0. So again, what happens here, this definition of Lie Cartan gives you full understanding or very explicit understanding of what development really means. So the development really is the key part of the development is solving this equation. So it's the key part of the development is constructing a curve in Lie group by a curve in the Lie algebra. And in the definitions of Harrisman, that's hidden, and it's hidden in the process of lifting the curves, lifting a curve from base manifold to the horizontal curve in the principal bundle. Because of course we all understand that when you lift this curve, you also have to solve certain differential equation. It's just not explicitly present. Here it's very explicit, and well, that's how you see the process of development. Now a question: why would we need this, and why I consider this development of curves as one of the key elements of Cartan geometry? As soon as we have, so in each model homogeneous space, we normally have interesting, so to say, interesting curves, or special curves, or curves that play a fundamental role for this model homogeneous spaces. In projective geometry, of course, such curves are straight lines. So projective geometry is in a way based on the notion of straight lines. If you speak about other model spaces like conformal geometry, where the model is conformal sphere, then one of the key objects in conformal geometry would be conformal circles, or if it's a split signature, then we would have null directions and null lines. So these are the objects we have in model homogeneous spaces. So development allows you to move this notion into your so to say, curved space. Sometimes we call space equipped with the Cartan geometry as a curved space or deformation of our model homogeneous space. So in projective geometry in particular, we have a pretty easy definition. So let omega be projective connection, then projective geodesic is exactly a curve that develops into a straight line. So again, there are other points of view on projective connections which are based on equivalence classes of torsion-free affine connections, etc. Then you would have different notion of a geodesic. Then it would be geodesic coming from affine geometry. Here it's a definition, and I'd say purely in terms of projective geometry. I do not reduce do not consider any affine connections related to a projective connection. And most importantly, it easily generalizes to tons of other examples. So whenever you have any Cartan geometry modeled by a homogeneous space, look at most important curves in your flat homogeneous space or model homogeneous space, and transform this notion into the curved version. So how do we understand what is the equation on for geodesics if you look at our connection form that sits on our manifold, base manifold? So as usual, we fix. So we fix certain section. So we apply omega to our curve x dot. So, and we end up with something that takes values in SLN plus 1. So, and as before, most important part sits here, because it is transformed linearly under gauge transformations. So now we could use gauge transformations because the image will be just one-dimensional space. So x dot is a vector, so image will be a vector here essentially. So we can use this section to fine-tune our section to make sure that this part is, for example, has this form. That would be even 1, and then all zeros. So we normalize our tangent direction, so to say, by approximate gauge transformation. So then we would know that if you now start integrating this curve, which is the curve x of t in the Lie algebra, we would see immediately. Yep.
You achieved it by that residual gauge transformation in G minus 1?
I use gauge transformation, so I use the same play game. So I replace my section by some gauge transformation. And this gauge transformation acts as full linear transformations on this part.
But where is the psi? Is it in G minus 1? Or
No, psi takes values in G naught. Psi takes values in G naught. So G naught is this thing, 0 here and something here. So this part will act linearly on this slot.
Okay.
And using these linear transformations, we can normalize the tangent direction to this particular form.
But I thought we already used that to put it in that nice form with
No.
system.
At that moment, I got back. I forgot about. If I don't even use any coordinates right now.
All right.
I don't use any coordinates. So if I use coordinate system, I can choose. This is a correct question. So if I have coordinate system, I can I can choose a section that brings this to this one, to this form. But then, and actually, I can compute this explicitly omega of x dot, and I would get here x1 dot, x2 dot, etc., xn dot, and then I start doing other gauge transformations.
Okay.
Because that's not what I want. I want this, and I'm still allowed to do any gauge transformations. It doesn't. So if I used gauge transformation to bring my form to this particular representation, this doesn't mean I cannot use some other transformations.
Gotcha.
Yeah. So what actually happens, the idea is that I normalize tangent direction now, and tangent directions determine straight lines. So if I want to know whether my development is a straight line or not, it's sufficient to require that if I did this normalization, then this slot also becomes 0. So this means that if I integrate this curve into curve g of t and apply it to the origin, my orbit will be exactly the straight line in this direction. So the idea is to write the equation on geodesics is, yeah, that's what I'm saying here. So the idea is that to write explicitly the equation on projective geodesics is as follows. Use gauge transformation to normalize your tangent vector to this form. And your curve will be projective geodesic if and only if after this normalization you also get zeros in the slots. So that will be your, in a way, conditions or equations on projective geodesics. And that's exactly what I'm trying to explain here. I'm skipping some part of very, very explicit calculations. Again, I can leave this for tutorials and would be happy to go through very explicit calculations, how it's done. You end up with this nice system of second order ODEs, where P1, etc., Pn are certain quadratic expressions in the first derivatives, which depend on your projective connection. And I'll show you this more explicitly in an easier two-dimensional space, two-dimensional case. And again, this formula is directly borrowed from Cartan's article on projective connections. So if one wants to dig into detail right now, you can pick up this article and read it. There will be a bit more explanation of this. So what normally happens is that you try to choose xn as a parameter on your curve. I didn't say much about the choice of a parameter, but the construction is the construction of development is invariant. It behaves naturally if you choose a different parameter on your curves. So it just reparameterizes. If you reparameterize your curve here, it will reparameterize your curve on the development of your curve. So if you assume that your parameter t is just xn, then you end up with this nice system of second-order ODEs. And these are equations on your geodesics very explicitly given here, where again P1, etc., Pn are quadratic, non-homogeneous. So it's something that is quadratic in first derivatives. It will have 0 first and second terms, but not higher terms. So this is a very special kind of systems of second-order ODEs that define your projective geodesics. And if you go for n equal to 2, it will be just one equation left, and this equation will be particularly simple. It will be just an equation where the right-hand side is cubic with respect to y prime. Y cubic because you get quadratic here, and plus and go to cubic in this term. So a very interesting question that I will be speaking probably already next time is whether or not, given such equation, you can actually reconstruct a projective connection, for which this equation defines your projective geodesics, and how unique this projective connection is. So, yeah, that's the next thing, to introduce another big, well, probably somebody already today will introduce a curvature for me and save me a lot of time. One interesting open question for those who would want to have some more challenging part of Cartan geometry. So I here wrote explicitly the equation on projective geodesics for projective connection on the plane. So if you have a projective connection on the plane, then you know that projective geodesics will be defined by this kind of second-order ODEs. What about other kinds of interesting curves in projective geometry? So projective geometry is, of course, based on straight lines, but there are other interesting curves in projective geometry. In particular, if you speak about plane, then the next interesting class of curves would be conics. And then the question, what would be the equation on, what would be the notion, well, we can immediately define what is a projective conic. That's fairly easy. So a projective conic is a curve that develops into real conic in the projective flat projective space. What is the equation for projective conics in this case? And again, a hint: conics are defined by fifth-order ODEs in the flat case. So one can expect that there would be some special class of fifth-order ODEs that is probably in one-to-one correspondence with some class of projective connections on the plane. So the question, what kind of fifth-order ODEs do you get? Again, that's a question, I'm not sure I know the answer to this question, first of all, but I know how to get to this answer, and the ideas are absolutely the same, so you can do some normalizations and reach to the point where you see which slope should be 0 to ensure that you are your developable, your development is a coin. Okay, so I stop here, and any questions?
Well, thank you very much. I'm impressed by a nicely full lecture hall. So, questions, comments? I mean, essentially, you can pick up any G invariant class of curves,
Yep.
right? And it will always give you some specific, special kind of curves on the curve.
Absolutely.
So are there some other interesting classes, but conics and lines?
On projective geometry, so we can probably ask Erwin. I'm looking for Erwin. So he was classifying some interesting equations in different homogeneous spaces, and each of these equations so would be transformed to some other unknown today interesting class of ODEs or systems of ODEs that in the curved model. So, and there are just, well, another very important class of curves are chains, of course, or chains are, but I will probably, as soon as you fix essentially your model homogeneous space, you get
No, I meant in the projective geometry.
projective geometry. Well, of course, so if you go higher, so then the next interesting class, of course, would be elliptic curves, yes? So then you have projective elliptics. You have no idea what is that.
Hey, Boris, does there exist an example of an interesting class of curves that does not arise from this type of construction? Or does this cover everything that is known?
Interesting class of curves in Cartan geometry, you mean?
Yes.
In general.
Oh. Well, of course, the notion of interesting is very vague, so.
Something that has a name.
Yeah, but I put it like that. I'm not aware of any other. So all examples I'm aware of can be defined exactly in this way.
I mean, as long as the class of the curves on the homogeneous space would be G invariant, then it comes this way, right? It's just a not very explicit way how to look at the developments. So in an absurd way, if you take any curve, take its orbit under G, you get a special class.
Well, not smooth curves may be an example, right?
Yeah.
Brownian motion, right? Because this makes us trouble with development.
Yeah, questions of singularities are actually very interesting. So what happens with singularities if you develop them?
I think also there are these sacred curves in 3D CR, dancing paths in 3D parasite. They're
Yeah.
sort of in the curve, in the flat, they're like the chains, but when for curved cases, they completely develop
Yeah,
into something
yeah,
different.
yeah. You get something very interesting. Fully agree.
Right, so any further questions? Not the case, let me thank Boris again. We shall go on with Rod's lecture in about 7 minutes.